Welcome to this explainer. Today, we're unpacking a really fascinating dual challenge right at the heart of modern power systems. On one hand, we've got the massive macro-level physics of balancing a global grid that's increasingly powered by renewable energy. But on the exact opposite end of the spectrum, we're dealing with the micro-level, incredibly precise mathematics of keeping individual humans safe when they're just standing on the ground at an electrical substation. We're going to look at exactly how engineers are managing this huge transition, making sure our push for global sustainability doesn't accidentally compromise local survivability.
Here's our roadmap for today. 1. The Renewable Stability Challenge. 2. Engineering Grid Inertia. 3. Substation Safety Mechanics. 4. Modeling Human Resistance. 5. Touch and Step Voltages. And finally, 6. Engineering the Ground Grid.
All right, let's jump into part 1, the Renewable Stability Challenge. So for well over a century, our traditional power systems were designed entirely around synchronous generators. We're talking massive, heavy, spinning turbines powered by coal, gas, or hydro. And those spinning masses provide mechanical inertia. It's basically a giant physical flywheel. If there's a sudden disturbance on the grid, that heavy spinning mass naturally resists sudden changes in frequency. But as we transition to solar panels and wind turbines, we're moving toward inverter-based resources. These connect to the grid through power electronic converters. The catch? They have absolutely zero inherent rotational inertia and they contribute way less fault current. We are literally removing the physical shock absorbers from our electrical grid.
So, what does this all mean? Well, without that rotating mass, our grids become incredibly sensitive to disturbances. A decline in system inertia significantly increases what's called the rate of change of frequency, or ROCOF. Basically, when something goes wrong, the frequency tanks way faster. Combine that with the natural intermittency of wind and solar, constantly fluctuating the power supply, and the introduction of bidirectional power flow from things like rooftop solar, and you've got a wildly complex system. On top of that, the lower fault current from these inverters creates weak grid conditions, making the whole system highly susceptible to voltage instability.
That brings us to Section 2, Engineering Grid Inertia.
Without getting bogged down in the heavy calculus of the swing equation, the crucial variable we need to focus on is M. That M represents the physical system inertia that we are actively losing as we retire traditional generators. To keep the lights on and the grid stable, engineers somehow have to put that M back into the math, even when the actual spinning mass is long gone.
And they're coming up with some brilliant workarounds to synthetically inject stability back into these weak grids. They're essentially creating virtual inertia. By using advanced control loops in grid-forming inverters, they can actually program solar and wind farm inverters to mimic the exact behavior of a heavy spinning mass. They're also deploying battery energy storage systems for rapid frequency response. And in some cases, they're straight up installing synchronous condensers, which are basically massive motors that don't generate any power. They just sit there spinning to provide that missing physical inertia and voltage support.
Okay, so we know engineers are mathematically and technologically stabilizing the global grid. But that brings up a really fascinating pivot. If the overall grid behavior is changing so drastically, how do we protect the actual humans interacting with the physical infrastructure? Let's zoom way in. From the macro-level global grid right down to the micro-level, the substations routing all this power.
Section 3, Substation Safety Mechanics.
Before we crunch any numbers, we need to clearly define the two main ways a human can be lethally shocked during a substation fault. First up is touch voltage. This is the voltage difference between the ground you're standing on and a grounded metallic structure you happen to be touching with your hand. The second is step voltage. This is the voltage difference between your 2 feet as they're spread apart on the ground while a fault current is flowing through the earth right beneath you. Both of these scenarios can absolutely be deadly if the engineering isn't flawless.
Section 4, Modeling Human Resistance.
Think about the physical reality of a person standing on a station grid touching a metallic structure while a massive fault current flows into the earth. To solve for safety, IEEE standards literally transform that human being into an electrical component. They use a Thevenin equivalent circuit, which simplifies the incredibly complex power system into a single voltage source and impedance. This lets engineers isolate exactly what happens to the human body.
It's a little morbid, sure, but absolutely fascinating. The safety of the grid literally relies on treating a person as a biological resistor, labeled as R_B, in a massive electrical loop. By assigning an accepted average resistance value for the human body, usually right around 1,000 ohms depending on the specific standard, engineers calculate the exact body current that will flow through the person during a fault. This ensures the physical ground grid is designed to keep that current well below lethal thresholds. And they don't just blindly trust the math either. To make sure these existing circuits are safe, engineers perform staged fault and integrity tests. They'll typically pump 300 amps of test current directly through the ground grid infrastructure. By doing this, they can hunt for high-impedance paths, weak ties, or broken underground copper wires. It's literally about finding the broken wire with test equipment before it finds a human being during a real fault.
Section 5. Touch and step voltages.
You don't even have to be touching a piece of equipment to be in danger. If a fault happens and you're just walking nearby, the massive current flowing into the earth creates a voltage gradient right there in the soil. Because your feet are apart, they're actually sitting at two different voltage potentials. And since electricity always seeks a path to balance, a body current can travel up one leg and down the other, driven completely by the voltage difference in the dirt itself.
Once again, the IEEE standard models this as a Thevenin equivalent circuit. By factoring in the human body resistance between those 2 feet and calculating the Thevenin impedance of the earth beneath them, engineers can pinpoint the exact maximum step potential. They calculate this as a percentage of the total ground potential rise to definitively ensure it stays well below the threshold that would cause a human heart to enter fibrillation.
Section 6. Engineering the ground grid.
Now, to safely dissipate these massive fault currents, substations aren't just built on regular dirt. They are constructed over highly engineered, buried copper grounding grids. When a fault occurs, the current travels down and spreads out across this huge subterranean mesh. That mesh lowers the overall resistance of the ground and evens out those dangerous voltage gradients we just talked about. But here is the tricky part. These grids have to be meticulously calculated and fully designed before a single drop of concrete is ever poured.
Because you obviously can't test a copper grid that hasn't been built yet, engineers have to predict exactly how the natural earth is going to behave. They use what's called the Winner 4-pin method. By driving 4 probes into the virgin soil at equal distances and passing a current between them, they measure the earth's natural apparent resistivity. This one critical data point is the absolute foundation of the math that dictates how much copper mesh is needed, how deep it has to go, and how thick the crushed rock on the surface must be to keep workers safe.
So we've seen how the macro grid is losing its physical inertia and becoming this highly complex variable system defined by the unpredictability of wind and solar. Yet, down on the ground, substation safety requires absolute mathematical predictability to keep human beings alive during a fault. So the big question we walk away with today is this. As our global grid dynamics become increasingly volatile and fault currents shift due to inverter-based resources, how will engineers evolve these foundational safety models? How do we guarantee that local human safety doesn't get lost in the global renewable transition? It's a massive clash of macro unpredictability and micro precision, and it's absolutely going to define the future of grid engineering. Thanks for joining me on this explainer. I hope it sparked your curiosity.